So hi everyone. So I'm Xavier. So you have both our emails if you need to ask any questions. So essentially, well, Theo said everything there was to say. We are going to discuss during the week problems that are exponential in size. Right. So our entire course is built around problems that are exponential in size, which means that if you want to do a brute force approach to solve them on your computer, classical computer, you need this amount of memory times 16 if you are using complex number, times 8 if you are using a real number. And so it's too tough. I mean, essentially, you just put numbers like n equals 10, that's 1,000, that's 16 kilobytes. Even I had that when I was a kid. 20 is a megabyte. Still easy. 30 is 16 gigabytes. So that's pretty much what you have on your laptop if it's recent enough. So on the laptop, you can do something between 20 and 30. 40 is 16 terabytes. That's pretty much it. And maybe you can do 50 on the biggest supercomputer on Earth or something like that. But I mean, this is exponential. Let's go on quickly. And so the question is, what can we do when we have exponential problems? So a lot of people have been saying that, well, we can't do anything, so we need to go to quantum computers. Like one route, quantum computers.
Okay, so you check if your microphone is on.
Actually, I know it's off because I didn't unmute it. Here it is. Yes, better. So that's one route. But there are other routes. I mean, on the one we will be taking during this week is tensor network. And so really we will be looking for algorithms to do things like solve Ax equal B, or find an eigenvalue, Ex equal lambda x. So the basic stuff that you learned in your linear algebra 101, but on vectors, on matrices that are exponentially large, right? That's the whole idea of these tensor networks. And so, well, essentially, I mean, tensor networks, they started like maybe 20, 30 years ago. I think it depends where you put the starting date. And there are problems which are extremely large, for which we could get a correct answer within machine precision. I think maybe the seminal paper, I mean, it depends where you can start with Wilson, the numerical organizational group, is actually a tensor network algorithm, even though it was not seen like that in these days, so he got the Nobel Prize for it. And he solved quantum physics, essentially, with this problem. Then came DMRG, Density Matrix Relational Group. So that's Steve White, 92. That was, I would say, the real beginning of these tensor network problems. And then suddenly people started to be able to do n equal 400, n equal 1,000, and get the correct answer. So that sounds weird. I mean, how could you do that? It's exponentially large. And it's like always in physics. I mean, if you have the most general problem, then you can't do anything. But the actual problem that we are interested in actually usually correspond to much smaller set. They have a lot of structure, and if you use this structure, then you can actually solve much larger problem. I don't know, an example of that, and I will use this analogy more than once. If you take a random picture, so you take a picture on each pixel, you take it randomly. You can watch billions of these randomly generated pictures, and they will look all the same for you, which means they look like noise. And the probability to see something that vaguely resembles an elephant or a cloud or anything is 0, but a very small 0. So if you take picture with your cameras, you can actually compress them. If you look at the size they take, it's much smaller than the number of pixels that you have. That's because the algorithm is using the fact that you are actually looking at a very, very tiny subset of all the possible pictures. And then you're taking advantage of the structure of real pictures to process them and compress them. And it will be the same idea that we will be using over and over. So the question is not really the size, but what's inside the size, the structure of this. I need example to illustrate these tensor networks. So I've chosen three, and these three are very peculiar. They are not the one, if you just download a random tensor network lecture on the internet, 99% of the time, the examples will be magnetism, quantum magnetism, or Hubbard model, for instance, in 1D. So problems linked to the quantum many-body problems, to quantum materials. Here I've chosen the first application will be quantum computer. So we are going to use tensor network to simulate quantum computers. To try to, so essentially the goal is that by today late afternoon, or maybe tomorrow late afternoon, we will be able to put something on the internet that looks like a quantum computer. Like if people submit a job, they think that there is a quantum computer behind the behind the door, even though it will be just a classical example. And I will use that's my secondary goal in these lectures, to discuss what really is a quantum computer, what it is supposed to do, on when and why maybe it's going to be useful or not, we'll see. But at least you will get keys to understand much better, I hope, what's really about all these things that have been pretended for quantum computers. So that will be my first example. The second one will be quantum annealers. Not sure whether there are two N or one. So quantum annealer is actually a weaker form of quantum computers that will bring me closer to the actual natural thing that people have been doing with these tensor networks. So now we will have an Hamiltonian. We are back to more common grounds for people that are used with fermions and these kind of things. And the third application has nothing to do with all of that, and I'm not sure how far I will be able to go, but the last application is PDEs, so partial differential equation. So we will be using tensor network to solve things like the Poisson equation, or I don't know, maybe the Schrödinger equation, probably the diffusion equation. I mean, partial differential equation. So these equations are everywhere in physics. Essentially, you can pretty much write anything that we know about physics within this concept. They have nothing to do with quantum computers and quantum annealers or quantum anybody per se. And it's really one of the latest development in tensor network. It's really the fact that there used to be techniques really for the quantum anybody problem, for the kind of things that we will get started with. And now they are moving towards pretty much everything. So you will see in the next few years, you will start to see tensor networks appearing in the literature in domains that have nothing to do with the now there are papers on plasma physics, papers on computational fluid dynamics, papers on this and this and that, still exploring, but it works so amazingly well that this will come into production pretty soon. That will be the three kind of applications that are. And so the lecture will be at a very, very slow place. I really want to bring the entire class here to the level of understanding where you can actually write your own code, you can understand all the details, and I've taken no shortcut. So if you don't understand something, it means that you should raise your hand and just I can re-explain, or maybe I just forgot something. But it's really supposed to be a lecture taking all the steps. Right? It's not like a big survey where you get the idea of things. In the afternoon, we will actually write code to implement the algorithm that we will be describing in the morning. So write code, you actually need to understand exactly what's going on. right? So there will be, so I've written some notes. The plan is to actually make a paper out of these notes. So that everybody, so I plan to submit it to SciPost lecture notes when it's totally finished. I have a proposal for you, for some of you, and the one that who wants. So essentially right now there is everything about the abstract material in these notes, but since it is a lecture about computational physics, at some point you need to show some plots that you know implement some algorithms on a computer and then run it and generate a plot, plotting something as a function of something else. I mean, that's what we get at the end, numbers. So my proposal is that for those who really want, I mean, if you don't want, it's totally fine. And you can actually produce one of the plots that illustrate one of the algorithms that actually we are going to discuss. And if I like the plot and we find that it's good and it's actually helpful to illustrate this thing, then I put the plot inside the paper and you get your name on the author list. For some of you to work harder in the afternoon. Exactly, so that's said. And okay. So before I start, I'm going to write the syllabus that you get the entire scope of the course in a bit more detail, that you see a bit where we are going. And then we just start with the beginning, like really slowly. Is it something of?
That's what
Right. So let's write the timeline. So the first thing I'm going to explain is quantum computers. From an abstract perspective, there are many, I mean, there are essentially two ways you can think about a quantum computer, plus one. One is you can really start from the physics. You can, like, let's say it's a set of spins in electronic spins in the Coulomb blockade regime, for instance, in semiconductors, or these are Josephson junctions for superconductors, or maybe atoms trapped in laser beams, or NV centers in diamonds. I mean, there are essentially pretty much every field of physics as a quantum computer, I mean, of quantum physics as a platform that is supposed to be the quantum computer of the future. So you can start from physics and build up. Or you can start from a very abstract quantum computer model, which is what essentially a computer scientist has been pushed forward. So very abstract. It's quantum mechanics really stripped to the bare minimum. There will be no space, no fermions, no bosons, no time, no energy. So very, very abstract way of thinking about quantum mechanics. And then from that, you can start building quantum algorithms like Grover or Shor or any quantum algorithm you will work. So what I will propose, I will essentially present this abstract thing. We will do no physics, not this type of physics, except that we will not do any algorithm. So for those of you that wanted to take the other course on quantum information, we will not go discuss Grover or any of these algorithms. I'll just discuss the setting, the quantum additivity settings. Like what is this vector of size 2 to the n? How do we act on it? So to understand, essentially, really the goal is to understand why it is hard or not, when is it hard to simulate it, this kind of thing. So that will be actually a pretty short part. I'm planning to be done in maybe an hour or so. So that will be quantum computers, the abstract point of view. Then I will explain what is a tensor network. So that will be a pretty boring part, but also pretty short. Essentially, I have to define a bunch of things so that you know exactly what we are talking about. And I have to define the network, the basic operations, contractions, factorization, so a bunch of things. So really the basic things that we'll be doing. A bit boring, bear with me for this time. And then we can start the real thing. So the first application we will, so I'm going to present the concept each time on a particular application that you actually see this concept in application on real things. So we will use tensor network to simulate quantum computers. So first we will, that's a brute force approach called the state vector, so brute force approach to simulate a quantum computer. So that's not going to take us too long, just to show that it's hard if you just don't think too much. Then we will start the first real one based on MPS, on MPO. So that will be our first real tensor network algorithm using MPS stands for matrix product state, on MPO for matrix product operator. So this will be our first real tensor networks. And this will be an exact simulator. So you do everything exactly, which means that there is still some exponential hidden somewhere. Exact. Also, this is exact. Exact in the sense of numerics, between the two. Okay, and then I will have some discussion about general tensor network approach to simulate quantum computers, also in the exact framework. So the whole idea of this first part, and I hope to reach here today, maybe, we'll see how far I am. The whole idea of this first part is, so first, it will teach you something about quantum computers. You will see when they are hard to simulate, when they are not hard. And it will teach you the basic way of using this, all these things that I have introduced here. Still, the main idea is not there. And the main idea, I already hinted at it before, is compression. We are going to compress this state. On compression here, something to do with low rank, some matrices being of low rank, or in the language of entanglement, we are going to be able to do calculation for objects that are not too entangled, moderately entangled. So I will, and that's when this tensor network start to be very, very powerful, because there are many, many objects in life that actually have this property of being low entangled. And when the property is present, then suddenly we can do exponentially large systems at a polynomial cost. So I will spend a lot of time, some time explaining so low rank approximation of matrices. So things like SVD, singular value decomposition. Maybe you have heard about this, this one. Some that are not so well known, like PRRLU, partial rank revealing LU decomposition, cross interpolation. These are start to be like dark corners of linear algebra. All these things are things that you may have seen in your undergrad, but probably you haven't, or so quickly that you forgot. So I will do that quite in detail. And then we can start to discuss general things about entanglement. Things like area law, essentially discuss when a system is entangled or not. And then we can actually revisit these things. So revisit these algorithms that were done in the exact framework, but now with some sort of compression. And then we'll see what it brings. Again, how it compares with quantum computers. So some sort of compression will mean that we're actually doing some sort of error. And it's a good thing in some way, because quantum computers are also doing errors. If you have followed the literature, everybody's like, oh, what is your fidelity for 1 qubit gate? What is your fidelity for 2 qubit gates? These kind of things. Now we are on par. We also going to have finite fidelities for the things that we do. And now we start to have a method that you can actually compare in a fair way with what the actual quantum computer is doing. And actually, it will allows me also to introduce all the actual algorithms that are used in day-to-day work by people. For instance, I will introduce DMRG, density matrix renormalization group. That's really the original algorithm of Steve White, except that I'm going to introduce a version suitable for quantum computers, not for finding the ground state of Hamiltonian, but it's really very close in spirit. Okay, so that will be the second part, all this compression. Okay, and then I will be already, I don't know exactly where I will be when we will be on that. Then I will introduce the second application, so the transverse field Ising model. So that's a quantum annealer. If you have heard about, for instance, claims by D-Wave, that they can actually solve a super complicated optimization problem. This is all based on this model, so we are going to discuss it. And for the advantage for me is that then we will have our first and last Hamiltonian. Right? Everything here will be written in terms of unitary matrices. Now we will at last one Hermitian matrix. Then we can ask questions we ask about Hermitian matrix. What is the ground state? So finding eigenvalues and eigenvectors. I will discuss also a bit the physics of what you can expect from a quantum annealer. People use the word quantum computers for things that are actually very, very different in essence. And so I think it will also help to have in view what you can hope and what you should not hope of these kind of machines. Then we can revisit DMRG. So now we are back to essentially what you will find if you download a lecture on tensor network. People jump directly there. The advantage of doing this route, well, first it's a bit new, and also it really allows to disentangle completely the tensor network aspect from the fact that we are doing quantum many-body. You will see. Also, you will see that quantum computers are naturally essentially, you have the tensor network that just comes completely naturally into the game, so you don't need to do anything. Here, actually, we need to work a bit to transform an Hamiltonian that is going to be written in second quantification, for instance, or written in using like a spin model into the framework of tensor network. It's not totally trivial, it's not very complicated neither, but that's okay. That's going to be the new part we need to build here. And then we are going to do to take a leap. We are going to introduce something that was, that essentially stunned me 4 or 5 years ago. It's an algorithm called TCI, tensor cross interpolation. You will get everything on the notes, so if you don't write down everything, it's fine. I don't know exactly how I'm going to give this note. I'm a bit afraid that if we send them now, people will stop listening. I don't know. We'll see. You can tell me what you prefer. So TCI is an algorithm to which, so it's a learning algorithm. So it's very, very different from everything we will have seen before. It looks a bit like machine learning, and it has a lot of relation with machine learning. And as an input, it takes an exponentially large vector, but that you explain that you actually give the algorithm in terms of a function. So for instance, you have a function that takes one index from 0 to 2 to the n, and it returns something. So but that you know how to calculate. So something that you actually know. You can write a small piece of code that for a given set of indices returns the value. It takes that as an input, and as an output, it gives you a tensor network, so a representation of this object in terms of tensor network. And then suddenly, it opens the door to apply tensor network to pretty much everything. Before, we knew only how to do tensor network techniques for problems that were naturally expressed in terms of tensor networks. Since we have this baby, now we can apply it to anything. Try to apply it to anything. I mean, you can, and it will always work, but sometimes it will be super efficient, sometimes it will be not efficient at all, depending on whether there is this internal structure that allows the compression. So tensor cross interpolation is really changing the game entirely, and this is why now we are seeing all these people, all these groups shifting very quickly towards this tensor network things. So once again, they have been around for a long time, but they have been super specialized to very narrow problems for 30 years, and now suddenly we can start to think how to apply that to many different problems. And so the application that we will do, one application, for instance, is if you want to do high-dimensional integrals. That's how I came into this thing. I've been doing high-dimensional integral all my life for calculating Feynman diagrams or pretty much many things you need high-dimensional integral. Pretty much any problem, you can write the solution as a very high-dimensional integral. Usually it's useless. Sometimes you can try to do this integral with Monte Carlo simulations. That's quantum Monte Carlo, essentially. And suddenly we have a new way using tensor cross interpolation to do these integrals. And it's extremely efficient. It's very different from Monte Carlo. So for instance, when you have a so-called sign problem, well, TCI doesn't suffer from the sign problem of Monte Carlo. So there are problems where Monte Carlo didn't work, and suddenly tensor networks do work very efficiently. So it's very important algorithm. I think it's okay. Right now it's still known by very few people, but in a few years it's going to be a major algorithm. So I want to use it to do a partial differential equation. So I will introduce something called quantics, which is how to essentially represent functions with tensor networks. Very simple, you will see. And you will start, there will be some link here with the beginning. For instance, for those of you that actually know a little bit of quantum computers, something known as quantum Fourier transform is quantum computing, which is a part of the Shor algorithm. So it's really deep into so if you have a quantum computer algorithm with an exponential speedup, with a probability which is very close to 1, probably 1 actually, there is a quantum Fourier transform involved somewhere. And quantum Fourier transform is actually the Fourier transform in this quantics representation. And so that's why when we have been able to put a function in this framework, we will be able to do Fourier transform exponentially faster than using the traditional FFT that is implemented everywhere in today's engineering. So I will introduce that, and then we will start using it for solving PDEs. I will give you a few examples of what you can do and the kind of speed up that you can get compared to state-of-the-art technique. And that will probably be the end. So I don't know up to where I'm going to go. It doesn't really matter. You will have the notes until the end. And if we stop here, it's fine too. I prefer you to be able to really follow at your pace than to just rush to the end. Okay? Good? Okay, let's get started. Is there a dry one?
You can use the big one. Oh.
But it's wet, so I'm afraid if I use it, then
if you use everywhere, then it makes you can paper than to. Because then it's on the.
Okay.
If you wish, I can play.
No, it's fine. It's fine. You have some. I can do it. Thank you. Okay. Right. Quantum computers, yes. So essentially, we are going to work with qubits, right? So whatever is the underlying physics, we will just retain only two states, which we call 0 and 1. Spin up and spin down of a spin. But it could be, for instance, if you know about transmont, for instance, the superconducting platform that Google is using, then it's actually a slightly anharmonic oscillator. So you have actually 0, 1, 2, 3, 4, 5, but they just keep using the first two and then ignore the rest. So we'll just have two states. Except that we have n of these qubits. So the most general state that you can write is, so you sum over I1, In. So I alpha is either 0 or 1. And then it's I1, tensor product I2, tensor product In, and then some coefficient. I call psi I. Most general state you can write. And this, I'm going to stop immediately writing it like that because it's really too tiring. I just write this one big cut like this. Just a change of notation because well, if I write this big, I'm not going to I'm going to spend the entire lecture erasing things. Okay. So that's it. And essentially, the whole appeal of a quantum computer is the fact that this guy has 2 to the n entries, so it's a huge vector. And potentially, you may be able to do things that you cannot do on a classical computer. And it's really the idea of entanglement. And the whole is much bigger than the sum of the parties separated. That's what quantum entanglement is all about. So the entire state is not described by each state separately, but much bigger object that contain all the entanglement. And if we can do that in a controlled way, if you can create this state, the state that we want, then maybe we can do things that we wouldn't be able to do on a classical computer. Okay? And then we are going to apply gates. I assumed, I don't know, so those of you that are actually physicists in training, can you raise your hands? I have an idea of, okay. So those of you that are not physicists in training, oh, you're all physicists, okay. So in quantum mechanics, we are used to have an Hamiltonian, right? And then we would write something like the Schrödinger equation with Hamiltonian, and then solve it, and then we would get psi of versus time, which is what you need to do if you want to actually understand the physics really going on, because this is what you actually know energies. You know energies, and you want to from these energies you want to infer what happens in time. Quantum computational scientists, they don't think in that ways. Suppose that you have actually worked this out, then you can actually you can write something like psi of certain state at time tn. Which I will write like this, right? It's equal to the evolution. What's the name of this guy?
Time evolution.
Time evolution. Sorry. Time evolution operator U between Tn and Tn minus 1 times psi of n minus 1. With U. So I'm sorry, this is where you see that I'm not a real professor, that I can't organize my blackboard correctly. And so I will write all on. On U, between Tn and Tn minus 1, is a time ordering operator times exponential minus I integrate between Tn minus 1 and Tn of h of t dt. So that's the physicist way of thinking about it. The computer scientists, they essentially are going to give themselves U. So they are going to decide on a few matrices U. And then that's your guy's job to find out some Hamiltonian, some pulse sequence, some that actually generate this U. Okay, so it's, the inverse problem is for you to solve. They suppose that it is solved, and they give themselves a bunch of U's, and that's it. This actually decide on the rules of the game. Okay. So there will be two sort of, and these are called gates. So you do behind the wheel, you do a pulse sequence, or so essentially you engineer the correct h of t to generate a target U. And there will be 1 qubit gate and 2 qubit gates. So I will explain in 2 seconds what it means. I mean, it means the obvious as the gates that actually apply on single qubit and gates that only apply on 2 qubits. Why 1 or 2? Well, clearly because nature give you a two-body interaction, so these are the things that you actually get. I mean, you have to relate yourself to the physics at some point, and so physics give you that if you engineer things correctly. Sometimes you can know there are also some 3 qubit gates. They are useful theoretically. They are not so easily to implement in practice, but we are going to stick to 1 and 2. And anyway, you can build the 3 qubit gates from the 2 qubit gates. So just a matter of combining these things. Okay. Is it okay if I write slightly smaller? Yes, okay. Otherwise, I'm just going to keep. So 1 qubit gate. So when I apply a 1 qubit gate on 1 qubit, it gives me well, essentially the two possibilities with some matrix element UJI. And this is a unitary matrix because evolution by construction. So now the question is, okay, what does it do on the psi, right? So I have my psi. I apply U on it, right? So remember I had I1. And okay, now I have to say on which qubit I actually apply which qubit I actually apply the gate. So I apply it on qubit alpha. Third qubit, right? So fourth qubit. So I1, I2, I alpha, the one on which I'm going to apply the gate. Then IN. On this I alpha, I'm going to put a prime just to make it slightly different. Okay, so initially I had I1, I alpha minus 1, I alpha prime, I alpha plus 1, IN. With the corresponding amplitude. And now I actually apply this. So I'm sum over J. Yes. And actually I can remove the prime. I get the solution. Here, I just took, I was a bit, maybe a bit, I took this, I applied this U only on the one in the middle. Which means that another way to write it is that now by psi in is really sum over I prime alpha of psi I1 I prime alpha in I prime alpha I alpha. Right. I'm actually doing a matrix vector product only acting on this particular index. Yes? Okay. So that's, and really that's what I want you to remember is that, okay, so you need actually to understand the details because we will be implementing this afternoon. So you need to understand exactly what it's doing on the wave function. But also you need to realize that what you are doing on a linear algebra point of view is that you are doing a matrix vector multiplication with a very particular matrix that actually act only on one. So you can really think of this vector as a big vector, but which has a block structure. On the matrix has this very particular block structure, where it's diagonal almost everywhere, on only one block as this non-diagonal terms that. So that's it for 1 qubit gate. On 2 qubit gate, now you apply to alpha and you apply to beta. And it's really the same thing. So now I'm going to do something nasty, which I can do because I have a blackboard. So now you have a matrix which is now 4 by 4. It takes this and turn to that. So now it's 4 by 4 because it acts on 2 qubits. And it's really going to be write this one properly. So here I have psi I1, I alpha minus 1, I alpha prime, I alpha plus 1, I beta minus 1, I beta prime, I beta plus 1, I n. I'm really acting only on these two indices. Extended to I beta prime. That's the second, so 2 qubit gates. On the 3 qubit gates, if we wanted to have them, you can. Sure. What it's showing you. So that's almost it. We have almost defined what a quantum computer is. We need to define one last thing, which is measurement. So measurement. Well, when you measure qubit, let's say qubit 1, well, it's the same if you measure something else. You have a probability to get qubit 1 equal to 0 or qubit 1 equal to 1, which is equal to, well, the square of the wave function. And you sum over all the other qubits. The probability to find qubit 1 in a 3D measurement as you learned it in Quantum Mechanics 101, a bit generalized. So the probability to find qubit 1 equal to this. And then when you do, it collapses the wave packet. It means that psi, so you have a probability, let's say when you do, so if you want to do that on your computer, you just throw, let's say you have P of 0, which is equal to 0.3, P of 1, which is going to be 0.7. You throw a random number. If it is smaller than 0.3, you decide that your qubit has been measured at 0. So you get I1, a value I1 star. Value that nature, I mean, there is randomness involved in that. And nature gives you one value. And your wave function now essentially becomes psi of I1, I2, IN, delta, I1, I1 star. Force, now the new wave function is unchanged, except that there is only one possibility for psi, which is the one that you have measured. And there is a small caveat. First piece of short is over. Let's see how many of them we need. You need to renormalize here, so that this guy is properly normalized to 1 for when you sum over all possibilities. That's it. We have a quantum computer. Okay? And so you can read there are books, thousands of pages. Actually, for some reason that I'm not sure to understand, they never write that. They never actually write this object. Psi is almost never introduced. I mean, I don't claim I've read all the quantum computers books, but I read a few and I scanned a few others. None of them introduce this thing because they are somewhere else. They are in trying to understand what they could do with it. So they are already working with special cases. If you want to simulate them, then of course you need to introduce this guy. And as soon as, so we will take somehow a middle view. We are somewhere between physics and computer scientist, the foggy part of quantum many-body physics. And you see, when you do that, well, suddenly it's pretty clear what a quantum computer does. It does a subset of linear algebra, matrix vector multiplication. What it does. It does a subset of linear algebra, matrix vector multiplication. Good thing, I mean, super good thing, exponentially large vectors. So potentially you can, do that on vectors that you would not even touch on a classical computer. Bad thing, well, at the end, you don't get the vector. I mean, you don't get this vector, which is huge. You get one sample of the distribution. When at the end of the day, you measure all your qubits, which is what you do, you just get one sequence of bits. So think about it. I mean, the space that you are exploring is 2 to the n. So let's say 16 terabytes for 50 qubits. 16 terabytes, it's a huge space. At the end, you don't get 16 terabytes of data. You literally get 50 bits, 50 0 and 1s. And they are not even, they are given also by random. So there is some randomness. So actually the amount of information that you actually really get inside this is even much less. I call that the I/O bottleneck of quantum computers. Here it's really the output bottleneck. There is less, I mean, there is also a problem with input, but it's less fundamental. But the output bottleneck is built in. And it's really why it's so hard to build a quantum algorithm. If you look at the quantum algorithm around, they are really a handful. I mean, if you really look at the real ones, 3, 4, 5, and all the rest are just variations of variations of variations. But they're essentially, I would say, three algorithms that I know of. And the rest are variations. And it's because it's very hard, because you need to engineer things in such a way that at the end you get something almost deterministic, which means that you need to find a way that all these things collapse, interfere, so that only your solution has a high probability. You can also not do that, but then suddenly you lose most of the appeal of having a quantum computer. Okay, and then also one last thing I'd like to say on quantum computers. The Hilbert space is huge, 2 to the power n. But there is no way we can explore all of that. I mean, we will start from a product state, and then we are going to apply gates. But if you really think about even if each of these gates is parameterized by like a few angles, if you add all these few angles together, you actually get the idea of the dimension of the space that you're going to be able to explore, and it's tiny. It's orders and orders of magnitude smaller than the total Hilbert space. So on this provable, you have actually states that it's known you would need an exponentially large number of gates to actually reach them. So another question is are the states that we can reach with the quantum computers the interesting ones. So it's actually when you start to open the Pandora box of what's possible, what's not possible, you realize that it's actually a very complex question. And there are, okay, I'm making a very tiny digression here, and probably I'm not going to pursue on that, but there have been a lot of discussions around Barren plateaus, if you have heard these terms. And if you look at it, people have realized that most of the states that you realize with a quantum computer, if you are not careful, are actually random states. And these random states have zero structure and are useless, and actually you can't even navigate through them. So a lot of problems that people have had in trying to apply quantum computers to quantum chemistry, besides the fact that quantum computers don't really work the way they are supposed to, is due to the fact that most of the states are actually not interesting. So you need to make sure that you really navigate in the interesting manifold of states. I realize I didn't introduce the actual gates that we will be using, so let me do that right now. And also I need to write one quantum circuit. Perfect noise, not too dry, not too wet. So 1 qubit gate, I'm going to just, what I'm going to say is just a bit, just a possible choice. I mean, you could use pretty much whatever you want, but typically, people use the Pauli matrices, which happen to be unitary. So 1 qubit gate, I only need to give a 2 by 2 matrix. Okay, the 3 Pauli matrices. If you look at them in detail, you realize that when you are on the x-axis, you stay on the x-axis. So you need at least one gate which is called non-Clifford, and we will use the so-called T-gate. Just a rotation of pi over 4 around the z-axis. Except I didn't forget. Yes, on one which is Hadamard. Essentially exchange the axis where from the eigenstate of z operator with the eigenstate of x operator. It's a possible choice. Actually, you don't need that many. I think if you have only 2 of those, probably Hadamard on T, you can generate pretty much everything. Yes. And we need at least one gate, one 2 qubit gate. Otherwise, we cannot generate any entanglement. I'm going to use a control knot. So control knot, if I write it, so now 2 qubit gates are two qubits involved. So one is a control qubit, and the other one is a target qubit. And when you apply the gate, you need to tell which one is a control, which one is a target. So I'm going to organize the matrix where I put the control qubit first. Okay, so if you write matrix like that, same thing here. The control knot, it does nothing if the first qubit, if the control qubit is in 0. So it applies just, if the first qubit is in 0, it just applies the identity. And if the first qubit is in 1, it flips the second qubit. So it applies X. That's control knot. Okay. And now let me write a quantum circuit. So quantum circuit is really the way you will, if you open any article on quantum computer, you will see something that looks like that. So essentially, you have one line per qubit. You initialize. Usually you start from a product state where every qubit is in state 0. And then you can start applying gates. For instance, you can put this one in, apply the Hadamard gate. Then you can actually apply 2-qubit gate. So this is control NOT. And this is a control qubit with this black circle, and this is a target qubit with a cross. So for instance, I can use this circuit. Okay, that's a possible circuit. And then at the end, you measure. So if you open any article on quantum computers, you will see drawings after drawings that looks like that. And it really means I start with psi 0, which is in this case 0, 0, 0, 0, 0. I apply U, the first one, which in this case is Hadamard on qubit 1. Then apply the second one. Which in this case is control X between qubit 1 and qubit 2. Then the second one, qubit X between qubit 1 and qubit 3. Cx between qubit 1 and qubit 4. That's my psi 4. Okay, so you really have done matrix vector product. Here I have written it in terms of quantum mechanics notations, but I could write the same for my big vector. And that's going to be the first thing we will do this afternoon. Essentially write a small piece of code that takes a list of gates, Hadamard on qubit 1, control X between qubit 1 and 2, and so on, and update this huge vector to actually follow the state in which we are. So it's going to be the first emulator or simulator or whatever you want to name it of a quantum computer. If you put that behind a cloud, nobody can do the distinction between that and real quantum computers. Only thing that it will be a bit slower if you have more than if you really want to pretend that you have a quantum computer, you have to time the things correctly. Make sure that it takes the same time if you have 10 qubits or 20. But otherwise, nobody can do the difference. Okay? I've had 0 questions so far. On one hand, this is not...
Yeah, short break.
It's a break...
That usually gives...
Okay, I will make like 5-10 minutes to finish this section, and then we will have a break. And again, if there is anything which is unclear, please ask. Yes.
There's one question. Simple, the numbers that appear on the top refer to time steps, right? So the
Yes.
is time step 0, and then
This is the initial state. Then this is first gate. So this is H here. Yeah. So I mean, I write it like that here to be super pedestrian. Usually, you just write the circuit and people know what to do. Yeah. You have to understand this to the core. Realize that this afternoon you will be actually writing your own code to do this simulator. So you really need to understand what's going on. Yes.
you said this is indistinguishable from like if you put this in a classical computer, this would be indistinguishable from a quantum computer. But I guess each time you apply a gate to memory, you need to store the state rows.
So this we will see this afternoon. I mean, maybe this afternoon actually. So there are different ways of encoding this state. Either you can have something where the memory grows, or you can have allocate a big chunk of memory right at the beginning. I mean, it depends. We will discuss this. There will be many strategies. And depending on the strategy, we have something which is exact or not exact. It may be exponential in the number of qubits, or it may be exponential in the depth, so the number of layers here, or exponential in the precision. So there is always an exponential somewhere. And so if you really want to pretend you have a quantum computer, you have to make sure that it will really look but that's not really the goal usually. But I mean, it's really doable. For instance, let's say less than 20. So if you want to pretend that you have a 20-qubit quantum computer, 20 qubit, holding the full state in memory is 16 megabytes, which is 0. And then the only thing that you would have to worry about is to make sure that if someone uses only 5 qubits, it should be the same time, same computing time. So you always allocate the 20, even if you use only 5. Otherwise, people might suspect that you are cheating. But I mean, so it depends what you want to do. We will discuss that in length. That's the part of I will do maybe at the end of today, depending on how fast I am. Okay? Yes. Okay, so yes, you can. That will be the first emulator that we will write. It's called I call it the brute force. The official name is a state vector simulator. Then you really allocate a vector of size 2 to the n. And of course, yes, you reuse this state each time. So it's 2 to the n, and that's it. But 2 to the n can be a big number. So you cannot do better than 50 qubits. Then I will show you a way to do 1,000 qubits. Using the fact that we start from something which is a product state. So initially, you don't need to store 1, 1 and 2 to the 400 zeros. And so that will be really the realm of using tensor network. So I'm not going to explain it now because right now it would make no sense. But in a few hours, it will make much more sense. But there is always, I mean, the thing that people arguing that quantum computers are hard to simulate are correct. I mean, at some point, there is always an exponential somewhere that is going to catch you. For the most general circuit, if you want to have a quantum simulator that can simulate any quantum circuit, you always will reach some limit at some point. Next question is that if you want a quantum simulator that want to simulate interesting circuits, and then suddenly the question is entirely open. And so this is what we will discuss the most, actually. And this, of course, it's hard to define in such a clear or neat way. So we won't have a lot of theorems, but we have a lot of clear cases where we can do infinitely more than what the theorem would say that we can actually do. Okay, so there is one last thing I want to say before we switch to tensor network. It's actually very not something very. It's actually pretty deep, but not very complicated. But I need to say it. I don't need a lot of space. So when Theo introduced me, he said that I was somewhat of a skeptic in quantum computers. It's kind of true. I'm actually much more of a physicist than a computer scientist. I really grew up doing quantum nanoelectronics, so essentially studying the things that became now the transmons or the semiconducting circuit, all these things. So in my own lab, there are people trying to build quantum computers. So I started to get interested in that when it started to become like a trendy on things to understand what it would take to bridge what they are doing in the lab, so the actual experiments, to what you would need to get this very nice model that we just introduced. Right? On something that you have to realize that it's an analog machine. I mean, the state is actually defined by certain numbers of complex numbers, right? So complex numbers, they can vary continuously. So when you are going to act on it with your gate, what you're going to really do in practice is send a signal at like 4.3 gigahertz for a given duration. And it's always going to be not exactly what you want. It's going to be slightly longer, or maybe a little bit too intense. Or maybe it's exactly what you intended, or close to, it never exactly this. but some two-level system somewhere moved a little bit, and then suddenly your energies of your two-level system is slightly different, not much, a little bit. But then it means that it rotates a bit slower or a bit faster. So you can't really do exactly what you intend, right? So after you have the state psi n, that's the one that you wanted. But then there is the one psi real that you got. On each time you do something, there is a little bit of loss of precision, right? So just because by construction, when you do something, it's always plus or minus 1%, 0.0001% or something like that, but it always with a certain precision. There is also the phenomena called decoherence. Decoherence is actually when you get entangled, but with objects that you don't control. So if you get entangled with this two-level system, if you get entangled with a phonon, if you get entangled with I don't know, like an electromagnetic wave, anything that you don't really control, it's called decoherence. But it's actually the same phenomena as a quantum computer. It's just that you don't control everything on it. Bottom line, you get a fidelity here, which is just the probability to be in the state you want. So it's psi real projected over psi, the one that you wanted, square. It tells you the probability to be in where you want it. You can do the same definition with density matrices to be more general, but on this thing, it decays exponentially with n. A little bit of information each time you do something. Actually, you even lose a little bit of information each time you do nothing. So here, I do nothing. But this nothing, I think I know my Hamiltonian, so I know exactly how fast it's processing around, because everything is rotating. But maybe it's rotating a little bit faster than I think, and I am not doing an error here. On here, on here, on here, on here, on here, everywhere. Here. Okay? And so it's really a race against time. You want to create entanglement. On this, we will understand a bit later today, because if you don't create too much entanglement, then we, with tensor network, will be able to blast the thing. So it has to be very entangled to be out of scope for at least highly entangled. That's a necessary condition. It's not a sufficient one, but it's necessary. So you need to build a lot of entanglement. But each time you do something, you lose a bit. So it's really a race against time. Epsilon. Right now, you will see numbers. So essentially, epsilon is typically, it's typically 10 to minus 2, 10 to minus 3. So the numbers you will see for the best hardware, typically, for instance, best hardware would be ion traps. But now IBM has very good single qubit gates also, 10 to minus 3. Sometimes you will see 10 to minus 4, but only for the 1 qubit gate, never for the 2 qubit gates. So typically you are controlled by the 2 qubit gates. These are the hard ones. Typically measurement is 1%. And also typically people will give you numbers that correspond to what is called randomized benchmarking, which means that you are only looking at 2 qubits at a time, and you do things in such a way that most of errors actually compensate. So for instance, you do a gate, and then you do the opposite gate, so that most of if you wind a bit too far in one direction, it will unwind the 0, 0 direction. So the number you can really remember is that if you really want to do an actual quantum circuit, so something where, I don't want to hear about the details, I want to do this quantum circuit, it's typically 10 to minus 2. Maybe a bit better, but not much. So 10 to minus 2, it means that if you have 50 qubits, you can do 2 operations on each. And that's it. You get exponential minus 1 fidelity, so already it's not very. And that's the Achilles heel of quantum computers. Decoherent, this guy. You want anything really useful, you would need this. epsilon target. So if you want really to apply any of the algorithm, and I'm not talking about the hard one, I'm not talking about Grover, or I'm not, but if you want to do something really useful, and that's the entering point, so the minimum number of qubits, and it's really when you start to do something that you don't know how to do otherwise, it's more like 10 to the 10. And we started at 10 to the minus 1.5 10 years ago. We are now at 10 to minus 2. You can see the progression, kind of saturating, but we are very, very far from this target. So if you remember two things about quantum computers and two questions you have to ask when someone tells you, oh, that's it, what is your precision? How do you deal with the I/O bottleneck? Only spits out very, 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 very few numbers. So there are very, very few questions where you are interested at the end on essentially a yes or no answer. That's essentially 50 bits. It's a bit more than a yes or no, but you don't get much more than that. Yes, okay. On just to leave the things a bit more open, computer scientists came up with an idea to actually bridge this gap from 10 to minus 2 to 10 to minus 10. It's called quantum error correction. I put a paragraph on it in the notes, but I don't want to dwell on that. But there are ideas of using many constructions where you use many qubits to build logical qubits that are more protected to decoherence than the original one you started from. So there are ideas, and this is where all the hope of the community come from, this quantum error correction. There is no free lunch, though. So right now, it doesn't really work. After years and years and years, I think like 10 years ago, I was in a conference called 30 Years of Quantum Error Correction. So it's probably 40 now. And we are at a point in the hardware where there is one experiment by Google where they managed to show that they could get a logical qubit which is better than the physical one. Twice better. So epsilon is twice smaller. But at the moment, it took 100 physical qubits to do one logical qubit, and they cannot manipulate it. You can only create a trivial state and wait to see how slowly it decays. You cannot. So they are still far from having a single of this logical qubit. And even this logical qubit, they have a 10 to minus 2 divided by 2, let's say. So they are not at 10 to minus 10. And so it's not clear at all whether it will work. I mean, it will kind of work. So the theory is correct, it's neat. But whether it will work in practice, personally, I'm very skeptical. Okay, I will end it for quantum computers. You get the framework. The goal of this afternoon will be to start simulate these things. And for that, we will need tensor network, and that we will do after, what time is it? So it's 25. Let's say we start at 35, 11 minutes. Perfect. And you can ask any question in the meantime or when we start. If you think about it very well. So essentially, tensor will be the generalization of linear algebra to objects that have more than two legs. So what do I mean by that? A tensor T is essentially an application from a bunch of indices. So if I want to be a bit pedantic, I would write like I1 goes from 0 to D1 minus 1, cross 0 to D2 minus 1, cross, etc., cross 0 to Dn minus 1, to a field that will be either real numbers or complex numbers, or it could be something else, but practice, this is the two we are using. So that's it. Essentially, a tensor is that's it. It's just a bunch of numbers indexed by a bunch of indices. And I will make drawings like this. I1, I2, In. So this one takes n values, d1 values, this one takes dn values. And you will see what is really fun about tensor networks is that we will end up doing only drawings. So in 2 hours, you will start making drawings yourselves on write very complex equations as drawings, and it will be actually much, much clearer than when you write the actual equation behind. So this right now is just a notation, but soon it will be much more than a notation. Okay, so in this sense, a vector is something like that. A matrix is something like that. And things start to be funny when you have at least 3 indices. And why so? Well, you will understand very quickly because when we start to make networks, we will draw things like this, for instance. Like this would be a tensor network. It will look like that. I will define that properly in 2 minutes. And you see that if you only have vectors and matrices, well, it's very boring with vectors, with matrices. The only thing you can do is this. It's not going to be very creative. As soon as you have 3 legs, suddenly you have no limit in terms of the number of graphs that you can build. Any graph you want. And so you can think about it as a generalization of linear algebra. And you will see that a lot of things that we are going to do, you could have learned it in maybe second year of undergrad or maybe third year at most, but there is nothing very, very fancy. What is fancy, it's just that it's been discovered late, so it's not yet in the undergrad curriculum, but I would not be surprised if it starts to be part of the undergrad curriculum in 10 or 20 years. It's really something that once you have it, you see it everywhere. Okay, vector matrices, more complex tensors. Now, okay, there are a few special tensors I'm going to introduce. I'll introduce them now for one is the Kronecker. The Kronecker, I have this, I write it like that. And it's just delta I, so essentially it's 0 except where all the legs are the same. So delta ij, delta jk, delta kl. Okay, and I will make a big point like that. We will use it all the time, so it's good to introduce special notation. And then there is a flattening tensor. On this one, so yeah, alpha I on j. And this one is delta alpha equal I dj plus j. And I don't explain you what it does right now. I will do it later. There are a few special ones. Okay, I've explained what is a tensor. Okay, so far it's just definition. Now we need to, we have 2 big things that we need to do with tensors, two operations. One is contraction, the second one is factorization. Let's discuss contraction. So contraction is a generalization of matrix multiplication. So essentially, if I have a tensor like this, another tensor like that, let's say this one is T, this one is M, I, J, K, L. This is actually equal to sum over K of T, I, J, K, M, K, L. If I remove this, you just get matrix multiplication. But here you have an extra leg. So essentially, it means that whenever I have two tensors, whenever I draw a link between one and another, it means I am summing over this index, as you would do in Einstein convention. And so this, if I do the actual sum, I get a new object, I don't know, I call it Tm. Now has three legs, L, J, and I. Okay, and so you can do the contraction, and you have a bigger object, because now if all the legs have size d, well, actually in this case, this one has d to the cube entries, and this one has d to the 2 entries, and this one has d to the cube. So in this case, it's the same size. But you can, if I take a more complex network, for instance, I contract this guy, everything, then I have here, each of these objects is d to the 3. So in memory, I have d to the 3 times 3 plus 2, which are d to the 2. And here, I have one big object, which is d to the 5. This takes much, much more space in memory than that. And here, I've taken 5. Let's see if I have a 6th one. I just add a little bit of memory, while here, it's the exponents that increase. And if I put here 400, then I have 398, and here I have d to the power 400. So if you do this thing like that, you contract, but you can see that this is it's the same thing, it's the same object. So this is a representation of that takes infinitely less memory than the big object, for instance, this one. Okay, so that's, and everything is going to be about that. I have huge objects, I represent them as tensor networks, so in terms of small objects, and then we are going to have algorithms that only work on the small objects. We're never going to do the big contraction to work on the huge object, because that's it. It just explodes the memory of my computer. So we're only going to work with a small object and do stuff to calculate things, get the number that we really want at the end, without ever writing the big object. Clear? Yes. Just checking that I'm not forgetting things. Okay. Couple of examples. So if I put a star here, it means complex conjugate. So what is this in terms of plain language? Any idea? Sorry? Yeah, that's a scalar product between V and W, between two vectors. Sorry? Sorry?
Absolute value.
So this one? Trace of a matrix. Just I assume that this one is the same as this one, so MII, and I sum over the link. This one is equal to trace of the product of the two matrices, so on and so forth. This one is actually the outer product of V and W. No summation, so it's this one is a tensor Pij equal to Vi Wj. Okay, so we have one of the two operations, contraction, and we need the second one, which is called factoring. Ah, no, there's one thing I need to say before. I will find out to put the right amount of pressure. When you have a contraction, I define contraction for a single index. Now, when you want to do a contraction of a full tensor network, you actually need to do it in certain order, right? And the complexity of the calculation depends strongly on the order. So, for instance, if you take this network, so this actually is just a scalar. This would be a vector. This would be a matrix. But right now, I have a number. Actually, this number is a winning number of a lottery. So I need to compute it right. And the question is, how do I do it? And so one way, and so also I will do a lot of drawing like that. I will just say, for instance, here I contract, which means I am summing over this guy. Okay, we will see this in the notes a lot. So I usually have something like that, and then I just contract. So if I do that, I get guy. Then I can contract this guy and continue like that. But you see that if I do that, in terms of memory, at the end, I have here a vector which is d to the 5. On the last step, I was something like that. So I have a matrix product between d to the 4 with d to the 5, and this one as 2. So in terms of, so this is a memory footprint. And in terms of CPU, so computational, it's d to the 6 to reach this last step. And it's 5 and 6 because I only put 5, the ladder was only 5 long. If you took a ladder 400 long, it would be d to the power 400. So you're back to your exponential scaling that you're trying to avoid. On the other hand, I could do it the other way around. I could, for instance, first do this. Then I contract this one. So if I contract this one, here you see you have one which is d square, and this one is d square cube. So the total memory that you get at the end you get something with 3 legs. So d to the 3, that's RAM. And the CPU is the total number of operations that you need to do is d to the 4th. Okay, then I absorb this one. So that I have a d to the 3, and then so at the end I am back to d square. And to do that, I was let's see, clear up a bit my drawing. So I was like that. Okay, so this one has 3, 4. So the CPU was the 4. And then I absorb this one. And then I'm back to the same thing, and I can continue. will never go up more than D3 for the memory footprint and D4 for the CPU each. So if I have 600 of them, the total CPU time will be 600 times D to the fourth, while here it will be D to the power 600. Bottom line, don't just contract them in any order. Usually there is one smart order and a lot of bad ideas. Okay, and actually finding the correct order is an NP-complete problem. So it's for a general graph. If I give you a general graph and you have to find what is the best order, it's actually complex. In practice, usually we can just look at the network and figure out very quickly what is the best way to contract. But you can't do it any order.
Is that the problem? Can it solve with an idea of quantum computer?
I'm sure, no, you can't actually. No, you can actually prove that most probably quantum computers can't solve arbitrary NP-complete problems. The answer is most probably no. That's what most of the post-quantum cryptographic things are using actually. It would be very strange if you could solve an NP-complete problem with a quantum computer. Generic NP-complete problem. You have to be very careful about these complexity statements because they are always about the worst case scenario. And it's never the case which interests us. So it's very, very tricky to handle these generic complexity statements.
It's just because you need one answer.
It's just because yes, it's usually behind all these theorems is like, okay, what is the most difficult of this class of problem? But usually you are interested in the actual class of real problem, and it's not going to be the random one. It's like the story I told earlier about pictures. The actual pictures we are interested are not random pictures at all. They are the one with much more structure. And this is never is never taken into account by this. They are very often they are misleading. I mean, you need to understand very clearly what are the hypotheses to use them properly. Okay, so we are done with contraction. Now we need the reverse operation, which is factoring. Okay, and factoring. This is where I will need my oops. No, actually, let me stay there. This is where I will need my flattening tensor that I introduced just a bit above. So let's say I have a tensor. Let's say with two index for the moment, ij. Actually, if you look at the memory of your computer, there is no such thing as a matrix in your computer. The way the things are stored in a computer is just one very long vector. You have an address, it's a linearly organized, and then you have each number in front of each, which means that if you have a matrix, so you have a matrix like this, the computer, what it's going to do is either it puts the columns one after the other. It's what you would do if you are using Fortran. This is the basic convention in Fortran, and I think also in Julia. Or it will put things one row after the other. This is what you do in C. This is what you do in Python. Doesn't really matter, but this is what you do. That means that what you're really doing is that you have an index here, alpha. It goes from there, then there, and then there, and so on and so forth. So it is equal to either I dj plus j. So this one corresponds to when I increase I, so this one corresponds to Fortran. And I will note it j tensor I because I'm a C guy, so I want to give preference to the C ordering. Or it's going to be alpha equal to j di plus I, and I will note that I tensor j. Okay. And it just these are the same numbers. It's just how you put them actually behind the scene in the memory. So you can flatten, so it's called flattening. It's actually, you can flatten a matrix in terms of a big vector. And so really putting one column after the other or putting one row after the other. Yep. So with this notation, oh, just bad practice, I should. And actually, most of the annoying things that we will do with tensors in practice when you actually write code is making sure that you have flattened the things in the right way. So my flattening tensor, really what it does is it takes I and j as the input and I product j as the output. That's what the definition I gave. Okay, maybe I mixed up with j tensor I, I'm not sure. Also, you can actually write the flattening of a matrix, for instance, like that. We have I, j, that's and if you contract this, since this is a delta, you actually get the flattened vector here, which is the same thing. It contains the same information as a matrix, but now seen as a long vector. If you implement this, you never want to actually implement this and then do the contraction by summing over essentially a lot of zeros on just a one. What you will do behind the scene is just reshaping stuff. It's because it's just really, you're not doing much with your stuff. You're just making sure that you understand who is addressed by whom. Okay, so this flattening thing, well, it's really, if I write it like that, it's really identity, right? Flatten and then re-put it in the original shape, or the other way around. So this, by this, I mean delta, alpha, beta. I prime, j prime, I prime, j prime, delta I prime, delta j prime. Okay, so I have a way to flatten or unflatten. Same data, just funny things. And now I can factorize. So for instance, no, I need one more thing. I need factorization. So essentially, what let's say I'm going to start with one tensor like that. First thing I'm going to do is space. Okay. Sorry. I can flatten it like that and unflatten it. And same thing here. Very badly with this is the same one, so I'm just applying this pair. Both sides, okay? So now if I only consider this part, so this here has been flattened into a matrix. And now I can apply everything I know about matrices. So the entire thing I've been discussing for the last 10 minutes is essentially you can map any tensor with 3 legs, 4 legs, 5 legs onto a matrix by grouping 2 legs together and the other legs together. You get a matrix. And then you can use everything you know about matrices. We will use factorization formula, so I will introduce them in 2 minutes. So for instance, we can write this matrix here, M, as a product of an orthogonal matrix and the upper triangular matrix. This is a QR decomposition. I will explain a bit where it comes from in 2 minutes. So I can have Q R. And then I can apply the unflattening here. And I get something like this. So that's a lot of bad drawings, and I really made the mess of it. I'm going to restate the whole thing. So once again, I have a tensor. I group together this and that, flatten them. I group together this and this, flatten them. It gives me a matrix. This matrix I factorize as a product of two matrices. And then I ungroup this upper two and this upper two. So this is equal to that's how I factorize the tensor. Okay? And I did it like that. So you will see in the notes, typically I cut like this. On I write, for instance, QR means write to group, factorize, ungroup. Flatten, factorize, and flatten. But I could also have done it in the other direction. So I could also have write it as it's a different factorization. I can do like that. Cut along this way. And I could also take this one together on this one, on these other two. And then I'm in trouble. I need to permutate before the role of the. Okay? Factorization. So it's essentially the contrary of contraction. And 90% of what we are going to do are going to be algorithms that alternate factorization, contraction, factorization, contraction, a few other things, until we reach this tensor cross interpolation algorithm, which is very different. It will be really just playing with that. We will see how powerful it is to solve a lot of problems. Really, what is amazing about this, etc. And so that's why it will be just mostly drawings.
Good. The intuition of this idea. So the factorization, you don't really get rid of any information.
So far, no. So everything I'm going to tell today, we don't get rid of any information. And starting from tomorrow, it's just restructuring. And already you can solve a lot of things exponentially faster just by without throwing away anything. And then starting from tomorrow, we will start to use this concept of compression. But I want to introduce later, first to get all the basic facts together, and then we will start compressing. But you don't need compression to be efficient. You can already do a lot of things without any compression.
You are actually the way that the Q and R have certain properties that you will kind of
yes.
Like.
So
it's always like that.
Yes.
But it doesn't have to be, of course. You can just factor it out everywhere.
So let me say a bit more about QR. I think I need a little bit more. So essentially, we will use three ways of factorizing matrices. One is QR. So this is a unitary matrix, and this is the upper triangular matrix. And this one I will explain in 2 seconds. The second one we use is SVD. You can write any matrix as a unitary matrix times a diagonal positive matrix times another unitary matrix. And the last one is a variant of the LU decomposition. So this is a lower triangular matrix. This is an upper triangular matrix. Yes? Lambda. This is a capital lambda. And this matrix is diagonal. But I will do both of these two in their turn in detail. This one will be important when we start to do compression. LU has to do with when you learn the Gaussian elimination in undergrad first year. Essentially, it was an LU decomposition. We'll do a variant which is called partial. So essentially, we'll stop the LU decomposition before the end. On rank revealing, that's the important part. Rank revealing means that we will get the most important part of the matrix. So that will be the compression. SVD, singular value decomposition, it's okay, another way to achieve the same goal. Compress the thing and get only the most important part of the matrix. So QR, you know, actually it's also something you learn in undergrad. You have a matrix A, and I write it as a bunch of vectors. So AQ is the Q's column, right? So when you do reorthogonalization, it's Schwarz no, I can't remember which. So anyway, when you want to create a matrix Q, so you want to create a matrix Q, which is unitary. So you say, okay, Q1 equal A1, but you need to normalize it. So you just divide by 1 square root of the scalar product. And then Q2, you want it to be a unitary matrix, so you need to be orthogonal to, so this will be A1, alpha A1 plus beta A2. So you just take A2, you remove the scalar product of A2 with A1 so that it's orthogonal to the previous one. Then you normalize the thing. And then for Q3, you just take A3 plus alpha A1 plus beta A2, and you just remove whatever it takes to be orthogonal, and then you normalize the thing. Is it clear, or I'm just very sketchy because I think you've seen that in undergrad? Just how you orthogonalize a matrix by just taking one column after each other and just making sure that it's orthogonal to all the previous ones. And since it is all with the previous ones, then you are making a linear combination of the previous, and this is why you get an upper triangular one here. You with me, everyone? Yes, that's QR. So it's just a fancy way of calling something that you have seen in undergrad. Okay, at the moment, I'm not doing any compression or anything, so I just need to be able to factorize. That's it. Later, we will seek a way to factorize, like we will have a big matrix like that, and we will want to write it like a very tall and skinny matrix times a very fat on the like something like that, like very tall and skinny, and this one are like small and fat, so that I'm compressing this. This will do when we start compressing, and this only work if this matrix is approximately of low rank. But I am anticipating here. I don't want to dwell into that this moment. For the moment, I just need to factorize. So write A as a product of matrices. Okay. I'm almost done. Let's see what I didn't include. Talk. Yes, yes. So I want to do one example. we'll do one factorization by hand, just to make it more concrete. Then we can start with the first algorithms. So control note. This control note. Actually, I said that it's so I wrote the actual matrix, but you can actually write it directly in terms of Pauli matrices, like this. So I said if the first qubit is in 0, you do nothing on the second qubit. Okay. So first qubit in 0, I can use. So this is identity on the control qubit, the Z matrix on the control qubit. This is actually a projector. If you look at this, this actually is equal to 0, 0. Projector on 0. So it's what happens if the first qubit is on 0. Is it clear? One is identity is this. Z matrix is this divided by 2. Okay, so control X is 1 plus ZC over 2 times 1 over the target qubit. But now if I am in the first qubit is in state 1, which now is 1 minus ZC. For the same reason, if I put a minus 1 here, you get 0 here and 1 here. Then I apply X on the target. Okay. So now, if I look at this formula, so I have control in, target in, target out, control out. This control X is a 4-leg tensor. Already out of my piece of chalk. I can write that if I call that AC 0, B target 0, AC 1, B target 1. This is sum over I of AC I, BEI, which I can write as A, I, B. This actually formula is directly a factorization in terms of 3-leg tensors. And actually, here, this is 2. The size of this is 2. So the maximum size here could be 4. But actually, it's only 2. So this factorization already is compression. It's exact compression. I mean, I didn't lose any information. But the control note actually has only, so in the language that we will use later, it has only 2 singular values, non-zero singular values. So already writing it like that, we have already gained information compared to the initial most general statement. Okay, so I have factorized by hand this control note gate. Okay.
By Austral,
if you make a very complicated 2-qubit gate, then it will be 4 in the index in the middle. I will come back to that when I discuss quantum supremacy, which I will do at the end of the exact simulators. And so now I want to make a very, very trivial statement. Is that, remember this quantum circuit that we wrote, for instance, this one. And I think I did it with maybe 4. By the way, is it clear what kind of state we get with this circuit, with many control nodes like that? Can you see it? So here, this H creates 1 plus 0 plus 1, 1 over square root of 2. And then I apply control node to all the others, one after the other. So with me, I do nothing if I am in 0, and I flip it if I am in 1. So at the end of this circuit, what I get is 1 over square root of 2, 0, 0, 0, 0, 0, 0, plus 1, 1, 1, 1, 1, 1, 1. The GSZ state. For the name of, I can't remember who. So if you measure the qubits, so you can make 600 qubits. If you measure them, you're supposed to find everybody in the same state, either 0 or 1. Trick question, is it a highly entangled state or not? If you open a quantum computer book, most of the time it will be called a maximally entangled state. And it's true in the sense that everybody is entangled with everybody. On the other hand, for tensor networks, this is a trivial state. And I would call it rather a minimally entangled, because less than that, it's not entangled. It's a minimum state that entangle everyone, but they are really not much entangled. And in terms of tensor networks, this is piece of cake. This I have millions of that only on my computers. Okay, but it's just a side. I'm a bit too early to explain all that. Okay, the statement I wanted to make is not this. I got sidetracked. The statement I wanted to make is that if you here put 0, because you initiate in 0, now these are tensors, J, K, L, whatever, M. Then I could contract this tensor network. And this is psi. Exactly the definition of what we have actually said before. So a quantum circuit is directly a tensor network. And just translate directly, you just take this guy, and you get a tensor network. The question is how to contract it. Actually get the number, which is your wave function. Okay? And that's why I chose quantum computing it's not one of the reasons I chose quantum computing to explain the tensor network algorithms, because it's very naturally a tensor network problem. You don't have to do anything to get into this format. Okay, I think we get everything we need. Let me just check that I didn't forget anything interesting. Yeah, no, it was this. Okay, I had one last comment. And then we can start with the bulk of, of the meat of the lecture. Done. So I need to put exactly the right amount of pressure. Too much and it doesn't go up. So the last comment I wanted to make is about control X, but it's very trivial comment. When you explain quantum X like that, it looks like it does nothing on the first qubit. It's just the way I said it, it was like, if you are in a state 0, you do this, and if you're state 1, you do that. But it keeps the qubit in the same state. It's an illusion. So I'm going to write the same gate, but now in the plus-minus basis. So plus is 0 plus 1. And this is actually equal to H, the Hadamard gate applied on 0. And minus is 0 minus 1. And it's the Hadamard gate applied to 1. And plus and minus, they play the same role at 0 and 1, but in the basis of the eigenstate of X operator. So X operator on plus is equal to plus. On X operator on minus, it's equal to minus minus. So the X operator in this basis is like the Z operator in the 0,1 basis. Okay. Bottom line, and Hadamard goes from H to plus, and then if you reapply it, you go back to 0. So it really goes from one basis to 0. Bottom line, if you can work out the algebra without X is equal to H D H. So if you change basis, it's X and Z operator exchange. And Z is equal to H X H. You can also multiply these matrices and check if you don't believe in the eigenstates, for instance. So I can rewrite this. So ZC, I rewrite it as HC 1 plus XC over 2 on HC. Okay? And the 1 minus ZC will be 1 minus XC over 2. And then the 1T here, I write H, apply the Hadamard on the T gate, and the 1 will stay 1, H squared equal 1, and the X will become Z. Okay? And why is that? And now, I can just write things a bit differently. The XC, I have one here, which is 1, and I have, the 1C. So I have one here, which is 1T plus ZT over 2. On the XC, I have one here, which is 1T minus ZC over 2. I'm just grouping things slightly differently. And now you see it's exactly the same one I had above, except that I have exchange control and target. So in the plus basis, the control target is the target basis in the 0 and vice versa. So don't believe that it does nothing on the control target. It's completely symmetric. And it's really like, okay, you have to think in terms of entangled things, not separate things. Of course, if you have separate qubits, then it does nothing on the qubit. But as soon as you have entanglement, then it's not true anymore. Okay, that's okay. So just a side remark, just to clarify things. Maybe I made them more confused. Now we are done with this tensor network introduction section. So you know everything you need to know for the moment to construct exact algorithms on the tensor networks. We will, I mean, of course, we need more concept, but the roots are there. Quite clear? Do you see in your mind how you could actually implement that in actual code? Let me actually make a quick survey for the early afternoon. Are there people in the room that have never written any scientific code? So any code to solve Okay, but apparently I asked the right one because nobody raised their hand. So everybody has, okay, if you have written something to solve some numerical problem sometimes, raise your hand. Okay, so I asked the right question. And who is using Python? Okay, Julia? Okay. C++? Okay. Rust? Ah, one guy. Well, he's in my team. Something else? Fortran? I hope no. No. Ooh. Okay, we'll see. Well, later you can use the language in which you are the most comfortable. Christophe has prepared things in Python. We have experience with. Essentially, you see, you will be playing with these kind of things. You will be grouping, ungrouping, contracting, factorizing. That will be enough for the exact algorithms. So now it's time to start an actual algorithm. This I covered already. Yes. What I'm doing this time? I'm half an hour. Okay. Okay. So we start with a brute force. Brute force. So this one is really to warm up us. I mean, if you look on the internet, you can probably download about 200 different brute force algorithms, full state vector simulators. And so the idea is that at the beginning of your calculation, you set up, you just allocate a huge vector of size 2 to the n. I write it like that, but of course you can see it as I mean, depending on which library you are using, you can actually directly write something like that, allocate this with n index. Or you can just have a big vector, alpha, and you can see alpha as I1 plus times d2 dn plus I2 times d3 dn plus I3 times d4 dn, etc., plus in. This is the unfolding of a vector. And if d equal to, which will be the case for qubits, then essentially this is just writing alpha in binary form. And this is really I1 times d to the power n minus 1 plus I2 2 to the power n minus 2 and so on and so forth plus in. It's written if you have the binary form of your integer, you directly have all the position of all the qubits. Okay? So this, in C, you would do that, for instance, you just allocate a vector of size 2 to the n, and then you would use the fact that you can retrieve any bits of an integer easily to know which place it is. So if you initiate everybody in state 0, so if you start from 0, 0, 0, 0, 0, then essentially this big vector here is 1 followed by 2 to the power n minus 1 zeros. That's your initial state. And we come back to your question that you had. Doesn't sound like a very, very smart way to initiate to hold this state in memory. So this is why we can do much better. On the other hand, here, we will have we can go very far. If you don't have too many qubits, you will see now it's going to be linear. The computing time is going to be linear in terms of the number of gates. Right, so we have the state here. We have the initial state. And now you need to be able to apply a gate. Okay, well, but it's really if it is a 1 qubit gate, just need to do this matrix vector multiplication. So it will be a bit of I mean, you're going to loop over 2 to the n guys, and only here you have, 4. I mean, it's essentially completely diagonal except for 4 numbers. So it's highly almost diagonal matrix. But I mean, you can do it this way. And the price is essentially 2 to the n times the number of gates. The CPU price on the memory is 2 to the n. Okay, so that will be the first thing we will do this afternoon. You want a code that takes as entrance the circuit. So for instance, one way to be the circuit would be, I want to have Adama on qubit 5. Then I want to have the X operator on qubit 3. The characters. Then maybe I want the control knot between qubit 2 and 5. That could be the way to have the input. And the output will be the state vector. Okay, that will be the first thing we will do. To warm up. Not very clever, not very fast. Still, a lot of people do that. I mean, if you have a quantum computer, the first thing we will do just to check that, because right now it's hard to get a quantum computer with which you can actually use more than 20 qubits. If you look at the nice experiments by Google and so on, they do have typically 100 qubits on the chip, but all the interesting experiments are done with 20. And even the 20, usually they use the one that are working best on this day. So you can see they have the chip and then they tell you we are using this, and this. Because it's actually more than 20 with the kind of epsilon that they get. It's no more. If you want to compare that to see that you are doing what you think you are doing, you full state simulator works very well. You can download one. I mean, if you try to, if you write quantum emulator, open source, you have a list and almost unlimited. Do we have a quantum computer if we have done that? Not exactly, because a quantum computer does not give you as much information. Like if we have 20 qubits here, we will have a megabyte of information. Quantum computer, once again, only gives you a sample. So you need to be able to sample your wave function at the end if you want to say that, okay, I have everything that a quantum computer has. You have much more in practice, but you want to be pedantic about it. You need to sample. Is it clear how you would sample this? Yes, no?
Great, because you can do repetition in quantum computer.
Oh, but you can run it several times and get several samples. Yes.
Yes, you build a probability distribution.
You can't build the distribution really because I mean, if you have a 40 qubit, once again you get 2 to the 40, which is 10 to the 12, and the number of repetition to get even one sample per bin. But you can get averages. And that's one way of using the qubit, for instance, if you're doing VQE, like variational quantum eigenstate, then you're doing something that looks a lot like Monte Carlo. And then you are actually doing averages. Some algorithms, like Grover and Shor, the goal is that you need to sample it once because it's done in such a way that the probability is super picked at the answer. But these are the algorithms that we can't run now. Okay. In the initial setup of the notes, and if you look actually at the syllabus you have on the website, I wanted to add to what I'm already told you, also other type of quantum-inspired techniques based on quantum Monte Carlo. I just removed it because I realized it was far too much material. So I won't be discussing this variational quantum eigensolver and stuff. That will be for or the night lectures. So just to write a couple of things, let me write. Actually, let me discuss quickly the Bayes formula because I will use it in several places. I already said if you measure 1 qubit, probability of U1 is the sum over I1, I2, IN of the square of the wave function. Right? And likewise, the probability to get I1 and I2, well, it's the same formula, but now I sum over only the last, I don't sum over the first two. Okay. And the same thing for P of I1, I2, I3. So now if you want to sample, you will use Bayes formula. So does anyone? So if you have the probability of A knowing B, it's equal to the probability of having A and B together divided by the probability of B. This you have seen, I guess, right? And so you will first sample I1, and then you will use the fact that P of I2 knowing, so this vertical bar means knowing what is on the right. So knowing I1 is P of having both I1 and I2, which I have here, divided by P of I1. So then I sample I1, I know it, then I can sample I2. And then I continue with P of I3, knowing I1 and I2. So on and so forth. So I sample I1, then I2, until I get all of them. Okay, so I have a clear path towards this. Yes, clear to everyone? Bayes formula? Google it. If you have never seen it before, it's Bayes it's very, very important things. Yes. Bayes probability, the Bayes inference, it's called often. But there is not much more than this, huh? Which is very is A and B. The probability of A knowing B is that you are in B. So it's number of things that you have inside this divided by the number of things inside B. So it's really fancy. I mean, of course, you can do that with measures and everything, but. Okay, so now we have the full state simulator. In theory, we will see how it goes when we try to implement that in practice. Okay, now we can start with the real one, the MPS definition. Okay, so now that's it. We have all we have passed all the long and the boring things. Now we have all now we can start to do fun things. So the first thing I want to introduce is called matrix product. Oof, and we are already at the third one. Product states. It's also called the tensor train because it looks like a train. That's it. That's the matrix for the state. And we will use, I mean, there are other tensor networks. I mean, there are many, many advanced tensor networks. But in these lectures, we will use mostly this guy and this friend matrix product operator that you will see in they are called the matrix product state, so MPS. In physics, and they have been called like that for 20 years by physicists. And then the mathematicians arrived and decided to give it a new name, tensor train, TT. I mean, really, I mean, but it's the same thing, okay? This guy. And so now the question is, we will have our state operator. The question is, can we write it? As an MPS? And the answer is yes, but it's not necessarily advantageous. So that will depend a lot on the problem. But always yes. And why? Well, very simple. You start with this guy. You flatten this, all this and these two indices together. Write this as a I2 tensor I3 IN. And you factorize it in some way. So I cut here. Factorize this thing into, so this is equal to, let's say I use QR, for instance. With the same number of legs as here, minus 1. So I did things properly. And then I take this guy, and I cut it here. Wow. 1, 2, 3, 4, 5, 6, 7. And I continue until I have my full MPS. Okay? So you can always put this into this MPS representation. Of course, the question is, what is the size of this index? If it's huge, then I didn't gain anything. If it's small, then I have a super efficient way of writing things. Okay? And so this, we call it the bond dimension. So typically, earlier, I called this one D. On the one here, we call it chi for the MPS. It's called the bond dimension or the virtual dimension. These ones, we call them the physical indices, so this physical dimension, and the bond dimension, so the virtual one for the vertical one. So the question is how much chi grows. At maximum, if I write chi versus I, so which let's say I equals 0, I1, then the first one is at most 2, and then it can at most grow as 2 to the power I, and it's also on the other side, it's also 2. So the maximum I can have is 2 to the power n over 2. But in most cases, what you really observe is something more like this. Then you can you have a huge compression due to the fact that you have not used the maximum possible. It's 2 to the n to the power 2, then it's a matrix which is 2 to the n divided by 2 times 2 to the n divided by 2, which is 2 to the n, and it's the same as it's even slightly less good as a full state simulator. But most of the time it will be much, much less. Okay? And now if we look at our state 0, 0, 0, 0, the initial state, Well, this is obviously a rank 1. This state, if I call it psi, so psi I1, IN is a delta I1, so sorry, you should do my notation, I1. So my state vector here is delta I1 0, delta I2 0, delta IN 0, which is clearly a product, so it's rank 1. So the initial state is a rank 1 MPS. And that's extremely efficient. It means that I have essentially 1 by 1 by 2. So I have n vectors of size 2. So if I have 1,000 of them, it really, the initial state, it really takes 1 kilobyte of memory to hold it instead of 2 to the power 1,000 using the full state simulator. So at least for the initial state, it's a huge gain. Okay? And so now we need to understand how we can actually apply gates onto this MPS and keep it into the MPS form. Okay? And I am, no, I have 10 minutes.
So I understand the problem with that. Let's say you want to simulate one computer and then you want to have a way to represent all possible states. And then let's say use this for the initials. And then the wrong way would be to that you okay, you know that okay, all possible states means that I actually have this good n base that I need to use. But then the initial state actually is kind of much more compressed. So I mean this
Product state, there's no impediment.
The wrong way we use this channel to the end.
Yes. Which is what many people do anyway. But yes, so exactly. So the matrix product simulator that we are going to sketch now, that we are going to implement, let's say, if we are fast in the second part of the afternoon, but probably it will take also part of tomorrow, is also exact. And you will see the cost is, I mean, can be much more efficient, especially if you don't have so many gates. If the depth of your circuit is very deep, then after some point, you may end up with bond dimension that grows so big that you cannot hold it in memory anymore. But that depends a lot on the depth, but also a lot on the kind of circuit that you are looking at. If your circuit is actually a quantum algorithm, a real one, usually the entanglement doesn't grow that much. That's an empirical statement. So you can do much more. So I will discuss a bit quantum supremacy experiments, all these Google things that you may have heard of. These are experiments that have been designed to be the most difficult ones to simulate, not to give anything useful. And as soon as you replace their circuit with something useful, you end up being able to simulate much, much larger quantum computers. So we will discuss all these things in turn. You're still with me? Not too tired? Yes? Okay, so I have my MPS, which is my full state, but not written explicitly, but written as an MPS. So in memory, you will have to store a bunch of 3-leg tensors. And initially, they will be 1 by 1 by 2, very tiny. But let's keep it general. I have this after a certain number of steps. Now, if I want to apply a 1-qubit gate, let's say Adamar on this guy. That's it. I mean, it's a local problem. I just need to do this contraction. Oops. It's I mean, I draw it slightly elongated because it's this contraction, but I mean, it's just a way of drawing it. So you can do 1 qubit gates, and it doesn't increase the bond dimension. You only act on one of these tensors. So 1 qubit gates are really trivial. And if you have only 1 qubit gates in your quantum circuit, it's trivial until you can do billions of gates if you want, which is just a traduction of the fact that there is no entanglement in your system. And if it's no entanglement, then why simulate a many-body things where you could just simulate separately what is happening on the different qubits? Okay, so you want to put at least some entanglement. And for that, we need a 2 qubit gate. So right now, because I have only 10 minutes left, I'm going to explain how to do it only on nearest neighbors. We'll do the case more general case tomorrow morning. Okay, but let's say I want to apply my control knot here. So in this case, it was okay. I will do the 2 cases at once because or it could be a general one. This one I already factorized, so it's even simpler than but you could have one which has not been factorized. So I'm doing twice. This is very bad to what I'm doing right now. You see? So here, I could just contract the upper part and contract the lower part. And actually, I'm already in MPS form because I can now fuse these two. If I want, I could just put my so I contract. I could use my flattening things in pair. And that's it. I am back to an MPS. I could do that because the control knot was already factorized. But if you do it here, so you contract this whole thing, you get something like that. Now you group this and this together, and you do a QR. And you're back. You have factorized your thing back to MPS. Okay, so it works with an arbitrary 2 qubit gate. So that's it. We know how to do 1 qubit gate and 2 qubit gate. You see it actually here. If you have a bond dimension chi and here a bond dimension 2, the biggest you can have here is 2 chi. So it can at most double each time you apply a gate. So if you apply a gate on every single 2 qubit gate on every single of these things, you will get a bond dimension which is 2 to the power the depth, which is number of layers, not the number of gates. You can so each depth is a number of qubits times the number of gates divided by the number of qubits. The depth. I mean, if you apply everywhere, of course, if you apply only on one, then you're only multiplying to the. So 2 to the depth, as opposed for the state vector, where it was 2 to the n directly, the CPU, but then it stayed to 2 to the n. Here it's 2 to the depth, and then when you reach a maximum, then you cannot go further. So the most that you can have, if you want, as a function of depth, here is something like that, until you reach 2 to the n over 2, and then you reach the state vector. So it's always better than the state vector. Even though if you really want to reach this regime, the state vector is going to be more efficient because you can really, so for very long depth, you can use the state vector. But otherwise, initially you have a very easy way for the first gate. And then the actual rank will depend a lot on the quantum circuit. Because at the end, it depends on the actual entanglement. This I will explain tomorrow, probably. It depends on actual entanglement of your state, and that's something depends a lot on your circuit. So it's depending on what you do, you can go maybe to much larger rank, but this is really the worst case scenario. Okay, I will stop here. We still need to see how to sample an MPS. If you want to pretend to be a quantum computer, we need to show that when you have that, you can actually sample it. And this we will see, it's very easy. And then we will need to show how to do a gate between the first and the last, or I mean, not nearest neighbors. And then we will have a full MPS exact emulator. It's actually useful. If you are in quantum computing, you want to have that in your toolbox, because then you can go, you can pretty much simulate anything that is of interest with available quantum computers. Because even if they are 100 qubits, since they cannot do many gates, you will be able to actually simulate this properly. Okay, we stop here. Do we have questions at this stage? No, we think it's crystal clear. We see. No, yes.
Just a curiosity. So these diagrammatic manipulations feel very similar to like the ZX calculus and those sort of diagrammatic languages for quantum computing.
I mean, ZX is also yeah, it's also a set of rules that you can transform this drawing into that drawing, and it's much less general, at least in the way it is used. But I have some friends that are trying to do something useful with ZX. So far, I have not seen anything. While this you can use to solve tons of actual problems. It's still very interesting, ZX, but no, it doesn't have the level of generality that this has.
I guess there the operations are much more abstract. It's just some set of rules.
Yes, and it's very linked to the Clifford algebra. So it's very linked to it's much more restricted in terms of the kind of problem that you have seen. Here, so far, we are doing things to simulate quantum computers, but later we will leave that and we start to say, okay, why should we do that? We don't have to follow, we don't have to use unitary matrices. We could use any matrices, and so we will start finding eigenvalues, solving linear problems, stuff like that, and then you will see how different it is. But yeah, it's kind of related. Carol, you had one also? No?
Yeah, just want to start on this threshold value of E. When the number of gates is number of qubits squared, that's the threshold value. So each time you apply a 2-qubit gate, the corresponding bond dimension can at most be multiplied by 2. For a control node, sorry. If it is a different one, it can be multiplied by 4. But anyway, there is a maximum at 2 to the n/2. This cannot be, the bond dimension saturates there, even if you put billions of qubit gate. So it grows exponentially, and then it saturates. This is a worst case scenario. What you may see in practice is you may see something like this. Or you may see, you may see a lot of things depending on the. How many gates do I need to make the most complex diamond stack?
I will discuss that in the context of quantum supremacy. So they have in context of quantum supremacy, they have thought exactly on this problem. Yeah. They didn't try to do anything useful. They tried to do okay, what can I do to be the most annoying to these computational people that are trying to simulate me? So I will discuss this a bit. Okay, well, thanks for listening, and see you in 1 hour.